So far, we have talked a lot about the general working principle of digital communication systems, and we've talked about symbols, and that there is a symbol mapping, and then that there is a modulation. And now we're gonna look at the modulation in detail. So what we have learned so far, that data is mapped to symbols, and now we get the symbols and we modulate them so that the symbols are put on an RF carrier which can be transmitted wireless or wired. And the first modulation which we are going to take a look at is the amplitude shift keying, or ASK in short. And this is the digital variant of the amplitude modulation, which you have learned in the last lecture. So let's call it just digital AM, but the official term is ASK, or amplitude shift keying. So here's a block diagram. So we get the symbols, we put it into the amplitude modulator, and we get the RF signal. And at this point, we don't care if the amplitude modulation is done in the digital domain or in the analog domain or both. We just don't care. So we just have a look at the general principle here, and we don't care about the implementation here in detail. So in fact, the symbols are digital, and this amplitude modulation can be realized, for example, by some digital signal processing, and then there is a digital to analog converter, and yeah, then in the analog domain there's a mixer, for example like here, up converter, and then we have an analog RF signal. That can be, for example, a real implementation for the amplitude modulator. But however, we don't care about this here in detail. We just want to learn how the amplitude shift keying works. So the input to the ASK modulator is a symbol stream. So here there's a set of two symbols. Yeah, so this is also given by this parameter km. So we have a symbol with two discrete states. And this in this example, these symbol states are mapped to amplitude values here, 1 for 1 and 2.0 for 0.2 for the symbol 0. And as the analog amplitude modulation, the amplitude level is changed according to the symbol. Yeah, so the parameter of the carrier which is altered here is the amplitude. So this is why this is the digital form of the amplitude modulation. And now we see the relation to the symbol period. So each symbol is exactly t-sim long, and this is the length how long the amplitude value of the carrier is retained here. So keep this value for 1 t-sim and this value for 1 t-sim again, and so on. So the symbol period is related to the frequency of the signal which is modulated onto the carrier. So here in the AM, the envelope was the actual signal which is modulated onto the carrier, and here this applies too. So the yellow line is the symbol, are the symbols over time, and the inverse of the symbol period is the symbol frequency, which in the frequency domain gives the bandwidth of the symbol, of the symbol stream. So this is the bandwidth. And as the symbols are rectangular functions, so the Fourier transform of the rectangular function is the sinc function. So you will find this in the lecture notes, the derivation. And what is important here, that here is the first 0, and this is approximately the symbol, the bandwidth of the signal modulated onto the carrier. And here's another example with more discrete states. So now we have 4 discrete states, and you see that you can encode more data into one symbol. In the previous example, if you consider binary data given by the computer into the symbol mapping, then we can decode 1 bit into 1 symbol. So 1 bit is 1 symbol here. But now with 4 discrete states, you can decode 2 bits into 1 symbol. So this is more efficient because the symbol period is the same. And so the bandwidth of the signal is also equal. So with the same bandwidth, you can transmit more bits. And actually, you can increase the number of bits. We can, for example, encode 256 bits into 1 symbol. So you can transmit 1 byte in 1 symbol, and this would be very efficient, but there is a drawback. As you see here, the spacing between the discrete values is much tighter than here in this example. So here you have more space, and this has one consequence. The signal with more discrete states is less immune to noise. I'll give you an example. If you receive a signal with this kind of noise pattern here, then everything is fine, because you can at each time decode the data, because the signal to noise ratio is quite good. But let's consider another example. You have this noise pattern. You see that it is now very complicated to decode the data here and to assign a value to the discrete symbol here. So you will have a lot of symbol errors or a high bit error rate. Yeah, so if you have tough noise conditions in your transmission channel, you need to choose a modulation with less discrete states so that the transmission is more reliable. Whereas if you have good noise conditions, then you can increase the number of discrete states and you can transmit more data in the same bandwidth. Yeah, and modern communication systems are adaptive, so they can measure the signal-to-noise ratio, and the transmitter and the receiver negotiate the number of states so that you always have an optimum of a good bit error rate and good reliability. Yeah, and an optimum between good bit error rate and a good data rate. Yeah, this is what I wanted to say. Yeah. So we have here 4 discrete states, and yeah, to each symbol here, an amplitude value can be assigned, and yeah, actually you see the amplitude values here. They are equally distributed between 0.25 and 1.0, and we choose a phasor representation here. So here it's very easy because we only modulate the amplitude here, but we do not modulate the phase. This is what we are going to do in the next video. And yeah, this phasor representation comes from this representation of a monochromatic signal. Yeah, here our sinusoidal function is hidden here in this exponential function. Mind the j here representing a complex number, and here the amplitude is changed, or the complex amplitude is changed, but only the amplitude but not the phase. Now we can plot each discrete state here in this diagram. So this is state, this is a symbol 0, 1, 2, and 3. So you see here, everything is on the real axis and on the positive side of the real axis, and only the amplitude is affected, but there is, for example, no shift here in the phase. Only the amplitude. So this is because we are still doing an amplitude modulation. Yeah, in the next video we modulate the phase, and we will come back to this phasor representation.